Okay, so good morning. So today the plan is the following. Today we will see how to model systems in classical mechanics. Okay, and the method that we will use is kind of will generalize even to quantum mechanics. It's just that the answers to certain questions will be different in quantum mechanics. So we're doing classical mechanics, and so there are two aspects of classical mechanics. Okay, so the first one is what we will call statics. Okay, so uh, statics refers to the variables that we need Okay, so to give a rough analogy, suppose you are interested in a play, and then first question you would like to know is where is the play being held, which hall, or something like that, right? So statics is a bit like that. And second part is dynamics. Here we discuss how does the system evolve. Okay, so we have to specify these two things, and so sometimes the word for the variables we'll call it how do you describe the state of the system. Okay. So we have to do step one is to figure out the variables, and step two is to give the dynamics, which is the time evolution. Okay, so this is what we would like to do, and so let's start with statics. Okay, as I mentioned, the variables that we need to describe the system. Okay, so we won't call them the variables, we'll call them the degrees of freedom. Okay, so the physics word for this is degrees of freedom. Okay. And of course, the variables need not be unique. Choice of variables. Okay. So question is, how do you do this? Okay. So using some coordinates. Okay, we'll just call them something. Okay, and like I mentioned, we'll call them generalized coordinates because they need not be like physical coordinates. They can have any dimension. Okay, so okay, so the classic example which you all know about is a free particle moving in space, and you want to model its motion. Okay, so in Newtonian mechanics, we will choose three coordinates x, y, and z or z. Okay, so here we can see that x physical dimension of y, physical dimension of z is what? Dimensions of length. Okay, so again, I mentioned this last lecture. In general, may not be okay. So example, even for this particle is, suppose I went ahead and chose r, theta, and phi. Okay, so this is a spherical polar coordinates. Okay, so what is the physical dimension of r here? Anybody?
Length.
But theta and phi are angles, they are dimensionless. Okay. So you can do this, but we are not done. We have to tell you the range. So we need to, this is not enough. We need to specify all possible values, all allowed values rather. Okay, possible is also good enough, I guess. Okay, so first let's look at the case of Cartesian. Okay, so now question to you is, what is the range of values x can take or y can take and z can take?
So minus infinity to
Let's pick x.
minus infinity to plus.
Okay, so we can write it this way. X belongs to minus infinity to plus infinity, or we write r, the real line, or we can be even more sophisticated and write x, y, z belong to r cubed. Now, let's go to spherical polar. What is the range of values for r?
From 0 to infinity.
Okay, r belongs to the half line 0 to infinity. Hopefully you all know the distinction between the square bracket and the round bracket, right? Braces. Does anybody not know this?
Yes, sir.
You don't know what this means. Okay. So this means, so this picture, this means that point 0 is included. Okay. So open set, closed set, this is like A, B is closed. Both points A and B are part of the set on the real line. So this is closed. If you have A, B, A is included, but B is not. If you have A, B open set, this is both A and B are not there in the set. Okay, so this is closed. Middle one is neither open nor closed. It's part open, part closed. Okay, so this is just standard mathematical notation. Okay, it's useful to write. And this means, the symbol means belongs to.
So the last one is open, right?
Yeah, this is, oh, I wrote closed. Sorry. Okay, so the thing is that, so this is what we mean by statics. So we need to go ahead and figure out what are the variables, make some choice, and then ask ourselves what are the range of values that it can take. Okay, so let's, coming back to this general thing, there's a example. So here n, I wrote something like this. So n, the number n is usually called number of degrees of freedom. Okay. So now let's go ahead and do a whole bunch of examples where you people have to tell me the answer. Yes. I can't. Snehil can't hear you.
Sir, can you hear me now?
Now I can.
Sorry, sir. So I was asking, would it be all right to take any possible any different possible range for the polar coordinates?
No, you cannot. No, you want a 1, 2. So it's like still the space is still R3, right?
Yes.
So you want to cover all points uniquely once.
So, suppose if we take r from minus infinity to plus infinity and then theta and phi from 0 to pi, would that make sense?
I need to think about it. Yeah, you have to just check that it is 1 to 1.
And then it will be all right if it is 1 to 1, right?
Yeah, but I would not recommend doing that.
I get that, sir. I was just asking. I get that, sir. Thank you, sir.
Actually, we are not done yet, so we didn't finish this part, right? So, yeah. So theta, what does theta? What is the range of values for theta? Snehil, since you are the guy trying something else, give me the regular values.
Sir, the regular values for theta 0 to pi.
Is it closed set, open set?
Closed.
Okay, very good. Okay. I like, instead of taking theta, cosine theta is probably a nicer variable, and that will just go from 1 to minus 1 to 1. Cosine pi is minus 1 and cosine 0 is 1. Okay, so cosine theta, this is just an alternate representation. I'll tell you in a moment why. What about angle phi? Anyone else? Nirmal?
0 to pi by 2.
Okay. Sayak Das?
Yes, sir. I think 0 to pi by 2.
Wow. Okay. Kaushik Pal?
Yes, sir.
What is the range of values for the azimuthal angle phi in spherical polar coordinates?
Sir, 0 to 2 pi.
Mm-hmm.
It should be.
Okay. And correct. I don't know where pi by 2 came from. But a question here is it open, closed, or mixed? Let's say I'll write something.
It is closed.
It's closed. Okay. But I will put it like this, and I'll explain to you why. Because 0 is identified with 2 pi. If I include 2 pi, it's like double counting. It's an angle. Okay, so this is true angle.
Thank you, sir.
Okay. So, but this is an interval. This is not a true angle, it's an interval. Okay. So, you might ask me why did I want cos theta? You see the measure in integration measure is dx, dy, dz in Cartesian, but this is equal to, we know, so this is, I like to write it like this, it's r cubed, r square only, correct? dr d theta, which I would write like this. there's a measure, right? Sine theta, d theta, and d phi. Right? This is something which you will know from elsewhere. Right? But this can also be written as r square dr d cos theta d phi. Okay, and if you did d cos theta, it's minus sine theta cos theta, but then you can take care of it by exchanging the limits of integration, because if you see here, phi gets mapped to this, and this goes this way. Okay, so switching off this thing. Okay, so this is kind of makes it go from this integration in the variable cosine theta is nicer. Okay, this is just some random remark which has nothing to do with with any deep stuff, but it is some calculational thing which I always remember. Okay, so now let's just we'll do more examples and okay, so let's do that, and you have to answer now. Okay, so first thing is a particle is moving in one dimension under the action of a force. Okay, so first step is how many degrees of freedom and what can we choose for it.
1 degree of freedom,
Mm-hmm.
and we can choose the position on this dimension that we have.
Okay, x, and that belongs to R. Real line. Yes. Okay. Anybody have questions here? And the key point here is, the force is irrelevant. We just need to know what is the force will be relevant for dynamics when we want to know how it's going to move. If it's at some time, then we need to write Newton's laws and integrate it and solve it. Right? So, second example is a particle moving freely in space on a plane.
To 2 degrees of freedom.
Mm-hmm. It's 2.
And in Cartesian coordinates, x and y, or polar coordinates r and theta.
Very good. Okay, so it's 2. So we can say xy belongs to r square, or let's write something, rho and phi. Okay, so rho will be again 0 less than or equal to rho less than infinity. And phi is an angle, so okay. Sometimes I will write a symbol circle for it. Okay, S1. If anybody has any questions, you should just interrupt. Comments also.
Sir, if a particle is moving freely in a plane, then its motion can be studied by considering it as one dimensional. Right?
How?
I mean,
How?
there is no force on it, so there will be no deviation in its trajectory. So the motion along with the trajectory along which it is moving can be considered.
It's a great question, and it's a pit into which everybody falls. Okay, and so let's ask ourselves why that is wrong. Okay, so here's the thing. So now the thing is, can you tell me which line?
So along which it was initially moving.
But we don't know all that. There is nothing to do with that. That's dynamics, right?
Okay, so we just know the initial point it was.
Yeah, that's all. So you require more detail. It could be any line which is lying in the plane. So we don't know that. If you take a different particle, if you have many particles, say, of the same type, they could all be going everywhere. They'll be moving fully in the plane. So So this is the thing, you should not think about dynamics. The dynamics may restrict it to go, I mean, a free, like you're saying, you already told me it's a free particle, so it's going to move in a straight line. We know that answer, but nobody tells you which line. That depends on the initial conditions and things like that, right? So statics knows nothing and doesn't care about that part. It's very important. Understand? Okay. So it's a great
Okay,
question,
sir.
actually.
Thank you.
Great question. Okay. So, okay. So now the third one is a particle is restricted to move on the surface of a cone. Okay, what is a cone? So let's draw something like this. So the cone has some angle alpha. Okay. So question to you is, how many degrees of freedom?
2 again, because the z can be written as a function of x and y.
Very good. Okay, so we can write. So you're saying, if you give me, so you're choosing coordinates x and y. Is that what you're doing?
Yes.
How do you determine z
Z is
from x and y?
Z square is equal to x square plus y square.
No, so let's do something. So let's say this cone's axis is z axis is this way, and the other two
yes,
axes.
cos of alpha into square root of x square plus y square.
How? So
Because
okay,
the
okay.
radius
So yeah, so here's what you're saying. Z equal. So now, so you're saying this distance is going to be x square plus y square, right? They will take the origin here. So this distance is x square plus y square square root, right?
Yes.
And this times this
cos of alpha.
cos of alpha. Perfect. Okay. But what is the range of x and y?
0 to infinity. No, minus infinity to infinity.
Sir, x can be from 0 to that radius of the base of cone, and y can also be that from 0 to the radius of the base.
No, it's like let's take the cone to go off to infinity. Okay.
Or then that can be from 0 to infinity.
Why
X and
0?
y
Then
goes from minus infinity to infinity. Z goes from 0 to infinity.
why? What about no x and y? Since we have chosen generalized coordinates to be x and y, we can.
Oh yeah, yes. We can't. We are not choosing r.
Yeah,
Like
it has to be
X
R2.
goes from
It has to
X
be
goes
R2.
from minus infinity to plus infinity. Y goes from 0 to infinity.
No, that's not correct. Even y should go. I mean, you just think about it. You look at it down. You can project onto the plane from here. Look down. Every point, any point on this will fall on the plane like this, right? Think of this R2. Okay. So because no way you can get minus y, no? A term which is minus, say y is positive, how are you going to get
I get that, sir.
Okay. No. Good to make these mistakes. Okay.
Yeah.
I mean, it's okay. We can also go ahead and choose Z and azimuthal angle phi. Okay. So so this angle will be like this, phi, and z is, of course, this z. Okay, z now goes from 0 to z is half line. So this is the intuition, yeah, something is half, but we don't think what is half. Okay, so when we did this half here, so when we look here, this is plus, always plus. Square root could have been minus also, that term is not there. Okay, and phi, of course, is an angle, so it is 0 to 2 pi. Okay, is this clear? So, any questions? Okay, so here is an example of a constraint. What is the constraint? The constraint is that particle lies on the surface of a cone. So we are not, when we are doing this, we are not asking how is it being kept there. Okay, that's not something which we need to answer. Okay, so we could think of this, if you wish, how would we realize, I mean, so something is making it stick to that surface. So we are not, there will be some constraint forces which you might need to do in real space. But, I mean, okay, but this is an example of a constraint. So suppose, so what is happening here is you would have started with x, y, and z, but then we impose this conical constraint, and we get 2 degrees of freedom, say x, y. Okay. So what we get is 2, which is the actual degrees of freedom, is 3 minus 1. So this is from the constraint. So this is, so simple ways, simple constraints which let you just reduce the degrees of freedom are nice ones. Okay. So we'll just call, when a constraint is of the form crucial thing equal to 0, something like this, we call it holonomic. Okay, so the example here is z is equal to, so we saw, so z equal to plus of square root of x square plus y square cos alpha is such a constraint. It's a holonomic constraint, right? Okay. And other constraints, we'll just call them non-holonomic. There are more detailed discussions you can look up in book. I'm not interested in them at this point. Other constraints, we'll just call them and holonomic, not holonomic. So we'll give one example of this. A particle is restricted to be inside a cubical box of side L. Okay, so it's something of this form. Okay, so we can go ahead and be clever and choose the axes to be parallel to the edges of these things. So we will be clever that way. Okay, but now there are constraints. So let's look at the x coordinate. What is the constraint on the x coordinate? So let's choose. So we can say x belongs to It's inside the box. Okay. Again, there's some freedom in choosing the coordinates. Instead of choosing 0 to L, I can do minus L by 2 to L by 2 or anything like that. But okay, I've done some choice. But you can see what is happening here, right? So here we can see there is a constraint. It's actually an inequality. So let's look at this. It says that x should be greater than or equal to 0 and x should be less than or equal to L, right? So these are all examples of anholonomic constraints. Okay, so usually anholonomic ones will not let you reduce degrees of freedom. So here the degrees of freedom of a particle in a box is how many? Somebody? 3, right? It doesn't go down. So this is just the general example. So let's look at a few more constraints. What is the number of, did I number the examples? No, I didn't. 3. So let's do an example 5. So example 5. It's an inclined plane. Okay, so on which there's a disk. Okay, so let's say that this is 0 and we want to, okay, so first step is to say what is the problem. We are told that the disk rolls without slipping. So question to you is, how many degrees of freedom? Bheraram, how many degrees of freedom?
So 1.
3.
Bheraram, how much? Then we'll get to Venkat Sai after that. You said something. Let me repeat that. That's all. Okay, Venkat Sai.
3, sir.
Give me, what are the 3 degrees of freedom?
I think 2.
It's the x direction motion and z direction, up and down, and
Okay.
rolling. Rolling about y-axis.
Y is out of the plane, so this is this arrow you're saying. So it is 3.
So y should be into the plane, right, sir? Right-hand system.
It doesn't matter, into, outside the plane, I'm not bothered about that. I'm just saying that, yeah, I'm not giving the direction. Yeah. Okay. Yeah.
Sir, A tan theta, x, y can be written in terms of J tan
So,
theta.
I mean, the thing is that first point here is that when it traverses a distance d, okay, and this is some known angle, right? This is an inclined plane with some known angle. Okay. Don't x and z get related? I think so. Okay. And y is not even playing any role, so there's no need for y. Y not needed. So I think it's 1 degree of freedom.
So it's rotating, sir.
Yeah, it can rotate. Yes. Yeah.
Rotating.
Yeah, it's rotating without slipping. So you can, yeah. So we can do one more thing. So we can choose an angle, right, with respect to this thing, call it theta. And but because it's a disk without slipping, d is related to theta by d equal to r theta. but theta is in radians. So we can choose, so the degree of freedom, okay. So question to you, is theta an angle here? Is 0 to be identified with 2 pi?
No, sir.
No, absolutely. Because 2 pi means it's moved distance 2 pi r away, no? It's gone, right? So theta is not an angle, okay? So is this clear what we are doing here? Okay. So this is without slipping. So just 1 degree of freedom. Now we go on to the next one. Same as 5, but disk rolls with slipping. So now how many degrees of freedom?
2.
2. Okay, because this condition is no longer true because of due to slipping. Okay, so it can slip this thing. Okay, so we'll have 2 degrees of freedom. D and theta.
In this case, it can slip as well as roll, right?
Yeah, it can do everything. It can do a mixture. Yeah, it can roll, slip, everything can happen.
So I was asking because if it doesn't roll and just slips, then
Then
will
it's 1
go
degree
back
of
to
freedom.
1 degree of freedom.
Yeah. So absolutely correct. No, I wanted to. It can do everything. Slipping is allowed. Okay, so then D and theta. So it's 2 degrees of freedom. Okay, so here this is an example of a holonomic constraint. Okay. Two particles moving in space. How many degrees of freedom?
6. 5.
Okay, somebody said 6 and somebody said 5. So we'll start with 5. Who said 5 and give me the 5? I mean, give some choice of coordinates. I mean, I'm not saying.
If
Okay,
there's
6.
constraint, then it is 5 degrees of motion.
What
If they are
constraint?
not
What
constrained, then
constraint? What is the constraint? What constraint?
I
Two
mean,
particles are moving in space.
like if
That's
the
it.
distance between the two particles is fixed on.
Have you said that?
I mean, if the distance between the two particles is fixed on,
No,
then it is
no.
not constant, then 6 degrees of freedom.
Yeah. So nothing has been said.
I mean, each
No.
particle has 3 degrees of motion.
Exactly. So R6, 6. Its degrees of freedom is 6. And it's R6, X, X1, Y1, Z1, X2, Z2, Y2, Z2. Right? Okay.
So in
Go
the
ahead.
first example, why don't we use the same reasoning as we don't know which part of the y-axis the disk starts, so it should also be a degree of freedom?
Yeah. So no. But it's some constant. It's boring. There's no dynamics. You're not doing that. We just said it's a disk.
Okay, sir.
Okay. So suppose instead of that we can say it's an inclined plane with some 3-dimensional guy moving. Then like you said, the y also comes into play, and you can add one more. Okay.
I get it. So we just removed it for our convenience.
Yeah. Absolutely. Okay. So the thing, the only thing which I'm trying to drive home at is that we should not be mixing up dynamics with statics, and this is something which will keep happening, and it's worth making those mistakes now. Okay, the Earth is moving around the Sun, okay, and treat Earth and Sun as point particles for simplicity. How many degrees of freedom?
Again, 6.
Who said 6?
I said Anna.
Okay, Ayanaba. Okay, good. Good. Anyone has any other numbers? Jyotiraditya?
Sir, I believe it's 2, sir.
Very good. Okay. What about Kanu Verma? Token. Subhash?
Yes, sir. I think 6 are there.
6. Okay. So Jyoti, let's start with you with 2.
Sir,
5. Rashmi Ranjan Bhutia gave one more answer. He said 5 because center of mass is fixed. Very good. Okay. So Jyotiraditya will start with 2. Okay. And so tell me what is the 2?
I assume elliptical orbits, so x and y coordinates for 2.
Okay. Very good. Very good. So here's a case of saying, okay, we know that, sun moves around, the earth moves around the sun in an elliptical orbit, and its sun is here, and earth is moving in this, and we'll call this the XY plane. Why not 1 itself, yeah? I write the equation of the ellipse also. Jyotir, why not 1? I'm being extreme now.
Yes, sir, I think.
Okay, good. Okay. So, thank you. So 1 is wrong, 2 is wrong, and let's understand why, okay? I wanted somebody to, and Jyotir, sorry, thanks for giving the wrong answer.
Dynamics is again included.
Exactly. So dynamics is the issue here, okay? First thing is that nobody told you where the sun is, okay? So sun is somewhere, so I require 3 degrees of freedom for location of sun. Okay? So actually, it could be 3 plus, plus 2 or 1, but we need that. But actually it is 3 for location of earth also. If you ask me, it's the same as 7. 2 particles are moving. Okay. I haven't told you what is the force. Okay. So let's see, elliptical orbits is consequence of dynamic. There is some gravitational force, etc. And that is causing something, etc. So on and so forth. So really, this is just simple R6. And it's exactly, the issue is the same as somebody said, when a free particle is moving in a plane, it's moving in a line, which plane? Okay. Same here. Who said what is XY plane? We don't know anything. It's going to move in a plane because some angular momentum is conserved. But what is the direction of angular momentum? It varies depends on the initial condition. Again, these are all details of dynamics. Okay. So we should not put those, the more we know about a problem, we mess up more. Because we do not learn how to separate statics from dynamics, and that is why I am kind of dwelling on some simple things, but it's important to accept that. Okay. So correct answer is 6. You can choose many ways. Go ahead.
So would it be reasonable to use the reasoning of problem 5 and say that since we are studying the motion of Earth around the sun, it's not as fun to know where the sun is? So
No. But the point is, at some level, then you have to choose some. Who told you why you should choose? Center of. Actually, the separation of variables which come naturally. There is not position of the sun, right? So like somebody pointed out, the center of mass coordinate is the nice one. So from the dynamics we know that. If you want decoupling, it won't be. So let's choose vector R1 for this fellow, R2. Okay, say masses are, M1 and M2. Okay, so I know what you're saying. So this capital R, which you may have seen many times, sometimes without logic, we will see Y, and little r we choose to be the separation, right? So it will be R2 minus R1. Okay, so what you are saying is that let's not worry about this. But again, that's dynamics, because we'll show that it's a central force problem. So they only it's a two-body problem, but it only depends on the separation. So the force acts in this coordinate, but what decouples as free particle is this. And you can choose and you're making a choice to choose center of mass to be your origin. Or whatever, right? The location of the center of mass of the Earth and Sun. So, but that is again dynamics. You're choosing a particular initial condition for the center of mass coordinate. Okay, so the naive answer is 6 and the correct answer. All these require much more sophistication. Okay, so let's do a few more and we'll end today's lecture. So two particles in space. Okay, such that.
So can I?
You go ahead.
So for the disk rolling without slipping, and for the case of disk rolling with slipping, the change in degree of freedom came about because for one D was related to theta, and for the other it wasn't.
It wasn't, exactly.
So,
it's no longer a constraint.
For that case, isn't it also coming from the dynamics of the system?
Yeah, so it's like this. So the point here, yeah, it's slightly messy, especially when holonomic forces come and you're able to eliminate degrees of freedom. Okay, so that's what I was explaining. To keep, for instance, go back to the cone problem, right? There should be something which you will want to, if a particle is in space, to keep it on the surface of the cone. There are some constraint forces, right? And what we are saying is we are not interested in those forces. That's all. Okay, so there is little bit of which are the forces we are going to consider and which we are not going to. So if there are holonomic constraints, we generally try to eliminate the things. Okay, so D equal to R theta is a holonomic constraint, and it's very easy to eliminate one of them. That's all. Okay, so okay, is that clear?
Okay, sir.
Okay, so we have two particles moving in space and their separation is fixed to be some, let's say mod of R1 minus R2 equal to C12, some constant. Okay, how many degrees of freedom?
5.
5, right?
5.
So 6 minus 1 holonomic constraint. 5. Okay. Quick, let's go a little faster. 3 particles and distances each of the separations. So C12, I am not defining it. It's obvious what it is. Are fixed distance, are fixed separations. How many degrees of freedom?
6.
Okay. So 9 minus 3, which is 6. So now we will become even faster. N particles. And mutual distances are fixed. Okay, so how many degrees of freedom?
3n minus NC2.
Okay.
3n minus NC2.
NC2 is n into n minus 1 by 2. Okay, so you can put in plug-in values. So let's put 4 first. So 12, n value is 4. 12 minus 4 minus 3 by 2 is it? Right? 4 into 3 by 2, which is 6. 5. 15 minus NC2 for 5, right? 5 into 4 by 2, 10, which is 5. 6. 80 minus 6 into 6 into 5 by 2, right? 15, which is 3.
Sure, sir.
Yeah, 1 second. I'm just going to show quickly that it's going to be negative, hopefully for the next fellow itself. So 7 into 6, 21, 0. What does it mean? I mean, these numbers are looking weird. If you can see for large enough n, 8 if you start putting, you'll start getting negative values. So this is not correct, right? Can't have negative degrees of freedom. 0 degrees of freedom also doesn't make sense. Yeah, somebody said something.
It should be 6.
Yeah. Okay, so this is wrong. And it is wrong in instant, this thing. And answer is 6. Okay. So let's, but it's useful to understand where we went wrong. I mean, so the mistake here is over counting. Okay, so you're subtracting too much. Okay, so if there is something like this, you know, such an object, we call it a rigid body. Okay, and again, we will see in this course, you may also have seen it before. For a rigid body, what you find is that the 6 are chosen like this. 6 coordinates, you know, 3 for center of mass and 3 for orientation. Okay, I don't know if you guys know, there's something called Euler angles. Okay, so what I have in mind is that, so you have some body with many particles, all mutual distances are fixed. That means it's like one hard thing, right? So what you do is you choose this your axis, and let's just draw some pictures now. So okay, so that will be one location of the center of mass, and so that is 3 degrees of freedom. And then you think of some axis which is soldered onto at the center of mass, which is on this body. And now you can ask, how can we rotate this axis? So there is this axis. So this is the lab axis, and this is the body axis. And we have to ask ourselves, how can they rotate with respect to each other? And these are what is called orientation of this axis, and these are called Euler. This can be chosen in the form of something called Euler angles. Okay, so rigid body dynamics, this is what you do. This is natural. We'll see this in this course. Okay, so I think I'll stop here and for questions. So is this clear what I'm saying? So this counting is not correct. You're overdoing it. It's a kind of fluke. It's correct for 4 also, but 5 onwards it gives you wrong answers because you're subtracting too much. Okay, so I'll stop here for today and pause for questions. Any questions? Okay, I guess this was very simple for you guys. Go ahead.
Sir, the idea of finding number of constraints always seemed very situational to me, sir.
Yes, it is very situational, dicey. What is constraint? What is this thing? If you are feeling very unhappy with it, yes. So, but think about it. Think about it in the following way. I mean, that you have tried. I mean, we have looked at examples which are kind of standard textbook things that you have seen over your years from high school, right? But what I have in mind is not that. What we have in mind is some totally new system where you have not seen anything before. And you want to ask, how do I model that system? Okay, so then you start looking and you make some, you could, for instance, take that, disk clipping you can ignore the holonomic constraint, d equal to r theta, but eventually you'll have to put it in if there are holonomic constraints, etc. So at the end of the day, you need to know what are the variables that you need. By the way, physics is very simple. You take subjects like biology or economics, okay? So they're trying to model population behavior, or or they're trying to model some virus or something, and that they don't even know how many degrees of freedom, how many variables they need for the problem, and then you can keep writing a huge number, but you don't know which is kind of relevant for for the question you're asking. So it comes down even to that, right? I mean, so for instance, we can have a molecule which is diatomic, okay? And then, so for some instances, you can model it by just as a single particle. So then you will say it has 3 degrees of freedom. But then you may want to say, no, there is this rotational degree of freedom. And so that is like a diatomic particle, which is 2 masses connected by some fixed length, say. Okay, so then you will say it is 5, no? Okay, so it depends on what we want to model also. Okay, so it comes down to really that. So you will make some crude approximations, but physics is simple, I like to say. Biology is hard, complicated for me, according to me, because we can. But you're right. I mean, there might be some nitpicking involved, in should I have chosen 2, should I have chosen 3, etc. But it comes down, at the end of the day, it comes down to the question we also want to answer. So there might be some dynamics of some variables we may not be interested in or something. Then we may we may have some arguments why that is going to decouple. Okay, sometimes it's the wrong argument also. Okay, so yeah, if you're unhappy with how one fixes the degrees of freedom, that is that's always there.
No, so it's not about being unhappy. It's just seems very difficult to get the right answer.
No, it's not difficult. It's not difficult. I mean, in the sense that if you're really modeling a system and you mess up, right, you will, in a real life system, you will find out very, very fast that you missed something.
That makes sense. Yes.
Okay.
Thanks.
Yeah.
Hello, sir.
Yeah.
You started the class by saying that this general coordinates doesn't have to be this same spatial coordinates or something.
Yeah.
So can it be like pressure, volume, and temperature?
Pressure, volume, and temperature.
I mean, can these things be done for thermodynamic system?
Yeah. So in statistical mechanics, which is the microscopic description of thermodynamics, there also you will have the same questions to ask, but you won't ask dynamics, but you will ask, temperature depend. You can do dynamics also, but usually you ask how things depend on temperature or something like that.
In statistical mechanics, we take a phase space, right?
Yeah. So there, see, the thing is that you do some coarse graining, etc., in those things. So that those are systems. Those are also classical systems, but where the degrees of freedom are so large that you are not particularly. So if you have, Avogadro number of particles, you don't want to sit there, like you name dogs. I have 3 dogs. These are their names. Okay. If you have 10 or 23 particles, you're not going to be name all of them. B, you're not interested in what is happening to one particle, but rather you're interested in asking properties of the collection of particles. So pressure, for instance, is something like that. So again, in statistical mechanics, the state of what you mean by state of the system is to specify some macroscopic variables. Okay, so this question which we asked in the beginning can be asked even in statistical mechanics, and we will. Usually in your stat mech course also you will. Okay, so that is true. So you'll be asking similar questions. What is the state of this system, and how do you specify it? So in those systems, these variables, again, you may, what are the independent, what are this thing? Again, those are things which we need to figure out. Okay, so pressure, you won't specify pressure and volume, say. You may specify only pressure, only volume. And so again, those things in thermodynamics is related to the kind of experiment you're doing. Am I doing a pressure experiment where pressure is being kept constant? Then, pressure is my control variable. Then that is what you want to keep. So again, there also you use those things, but we are doing much smaller, simpler systems. So whatever I said in the first slide is true in 3 different subjects. Okay, but the kind of questions you ask in each one of them, the answers are also different. Okay, so it's a very, very deep question and wonderful. Okay, anything? Okay. So let me first stop recording.